First of all, as a quick introduction for, as I mentioned, technical, but also for legal reason, I cannot play a song, a certain song on this speaker right now. So if you could just, in your head, play the first 2 bars of Heaps Don't Lie by Shakira, that just will help set the tone.
What if we don't know
Oh,
that?
well, ask your neighbor, just follow his... It's fine. All right, welcome. So we're going to talk about memory allocation. So who here is interested in memory allocation? Please raise your hand. Okay, that's most people. Who is interested in performance? Who is interested in Shakira? Okay, you're my audience. The other ones, you're just a bunch of nerds, but I guess we're going to have to oblige for once. Cool. So, as every good talk that I try to write, it starts by I read something on Twitter that is egregious and it upsets me, and I try to get into a rabbit hole. And that one was a quote I read. I don't know if you ever come across something like that, either like even on a code standard or like a discussion with a fellow member or senior, or just someone on the internet saying like, "Hey, don't use malloc." Anyone has ever heard like a guideline or something just like, "Just don't use malloc"? Oh, okay, I have some people. Some people sometimes see something a bit more like reasonable, like don't use malloc while the plane is in the air. You know, like you can malloc, but as soon as someone starts the takeoff, say like a procedure, just don't. I don't want to take the risk. So I try to delve a bit into this and figure out where's that coming from, and there's some somewhat reason, and I'm on the end, I think maybe tail end of a discussion about performance through my talks. I talked about profiling, I talked about multi-threading, I talked about caches and data locality, and finally we talk about memory allocation, also in regard to performance, but that's kind of the end of a long series. By the way, hi, I'm Matthew. If you've never heard of me, I'm a programmer, a game developer, and I used to organize some meetups. I help sometimes the Stockholm meetup and the Stockholm Game Dev Meetup. If you ever in Stockholm, feel free to reach out to me. I'm sure we can slot you in one of those. And I'm recently available for consulting and training. So, you know, if you have anything, feel free to reach out to me. I have many handles. None of them match. I learned the tip from Kevin Henley that you're supposed to check when you name your kids. Try to find one handle that is available on every platform. But it was too late for me. I'm born in '84. Anyway. So this talk, we're going to talk about how does the heap work, because if we're going to have to see if they actually lie or don't lie, we need to know how they work for that. I'm going to try to give you 10 guidelines. My flow is about 10 guidelines for memory allocation, and hopefully, whether you're a beginner or an expert, you'll find some of them that you found interesting or didn't know about. So, you know, hopefully we can make some sort of a bell curve with the whole audience about how useful you felt those guidelines were. All right, so first, what's in a malloc? Who here thinks that they know how malloc works? Okay. Who thinks they can re-implement malloc? Okay. Who thinks we can re-implement a good malloc? Okay, we have one brave man here, and as the rest was like, okay, I think we have maybe like a couple % of the audience was like, oh yeah, I can probably make malloc, and then one very brave man there was like, I can make a good malloc. I suspect maybe you have actually. Yeah, that's cheating, but you know that's what you get for conference audiences. You have the guy in the room who invented the thing you're talking about or something equivalent. So just some scope, because we only have a bit less than an hour. When I'm going to talk about initialization today, I'm going to talk about the act of reserving uninitialized bytes. So you could argue this is a C talk. I don't really do C, so it's still a C++ talk, but don't talk to me about constructing object or zeroing or none of that nonsense. It's just like malloc, basically, or whatever new calls to get 3 bytes. This is really what I'm focused on here. If your constructor has performance issues, this is a different talk. Same thing for the allocation. I'm concerned about how fast would it take to free those bytes back to the library or the OS. I'm not concerned about how many destructor you're running and how much side effects they have. If you decide to lock a mutex in a constructor, that's not the talk. All right, so since we're going to talk about performance, I think it's good to start with a reference, like what is fast? What is a fast allocation? And in my experience, looking at allocating on the stack is usually a good frame of like how fast can you go? Because for those of us who need a quick refresher on CS 101, this is your stack on a program, right? It grows down, then it looks up. There's historical reason. I'm not going to delve into that. But basically speaking, you have a stack. It starts at some point, and then you just keep pushing stuff as you go. If we reach a function scope, and every time you need to allocate a local variable, you just put it on the stack. And what does that actually mean? You take a pointer to the current stack, and then you increment it for the next allocation, and that's it. You're done. So for the assembly people in the room, allocating on the stack is basically a register add, which, as far as I'm concerned, is one cycle. On some architecture, it can even do that in less than one cycle. Like modern Intel CPUs and ARM can do several of those per cycle. You have 2 to 4 billion cycles per second, depending on your CPU frequency. I'm not going to say free because there might be a guy who's going to disagree with me, but it's almost free, right? You have nothing to do. You don't have to call a library. You don't have to call an operating system. Just one register add to like RBP or SP or whatever it's called, and you're done. RSP or SP or whatever, your stack register. And that's done. There's not even a cache involved. It's the fastest it can be. Of course, if this was amazing, we would just say, okay, cool, always use stack allocation, and then my talk is done, and you can all go grab coffee. But there are some limitations. The most obvious is compile time limitations. When you do a stack allocation, your compiler translates that into add whatever size you need to the stack pointer. So for the compiler to be able to emit that code, it needs to know the size of what you are allocating. And this is one of the first things they teach you when you start doing C or C++. You cannot have a variable size array on the stack. You can come back with me afterwards about some specific exception, but roughly speaking, you cannot. You have to know the size at compile time, which already limits the scope. Because if you have a container, you can't put it on the stack unless you have like an upper bound that you can determine. And also, it's limited in space. There's this famous website that is slowly replaced by AI called Stack Overflow. That comes from the name, right? There is so many space you can have on your stack, and once you overflow it, bad things happen. It has one advantage, though. Almost advantage, could consider the limitation. It always reclaimed at scope exit. When you exit a function, everything that was pushed on the stack from that function is gone forever. The bytes are reclaimed. Again, destructor or not, that's not the talk. But the bytes are gone. You can be reusing them afterwards. That part is great. Unless you want that memory to persist. And then we have another limitation. It's not only limited in space, it's also limited in time. It can only work for anything you call from the moment you declare the variable until you return. After that, well, hopefully your static analyzer will catch that you're returning a pointer to like a stack allocated variable that is now dead, but bad things happen. So we need to look at other options. But still, that gives us our first guideline. If you can, prefer stack allocation when possible. This is the fastest thing you can do. It's one cycle, and you're done. Cool. But obviously, that's not great for many programs, so we solved that a long time ago by introducing things like malloc and heap allocation. And it's great because you can allocate as much memory as you want. It's basically as big as the number that you can pass to malloc, which is a very big number. And unlike the stack, it's not automatically reclaimed, which means it can leave as long as you remember to call free. Or don't, and then it's going to live forever. But, it's not limited in time, which is an advantage for obviously some cases. And if you still, and you should, because this has been taught to people for like over 20 years now, you should use something like unique pointer ideally, so have some form of reclamation to make sure you don't forget to call free or you don't call it twice, things like that. So you can still go back to some kind of a scope behavior like the stack does, but you can move it around if you don't want it to happen immediately, etc., etc. So we can emulate basically stack allocating memory with infinite amount of space, roughly speaking, and arbitrary amounts that are not known at the compile time. That's great. But now, how does that work? How does that actually work? Well, I think we had a few people who had some ideas about how malloc works. We'll just walk through this together, right? So usually, and I'm talking like on average in some run-the-mill, like maybe malloc implementation you can find on your OS. So there's usually like your standard library, your C library will have what's we call like a free list, like a list of blocks of a given size that's available for allocation. And we'll try to grab the first one that's available. And luckily, it's there. You have like, I don't know, like you recently freed or reserved like 16 bytes for allocating 16 bytes. You just return the first in the pointer, you mark it as used, and you're done. That's pretty good. But sometimes you don't have that because the buckets are full. So what you do is you grab a new bucket. It's called usually pages. Most allocators nowadays, they chunk. They have a bunch of buckets per size, power of 2s most of the time, from like 8 or I think usually from the minimum size of malloc, which is 64 bytes. Max 90. There's a define somewhere that tells you what's the minimum size that malloc usually aligns for, and that's the minimum size you should be caring about when you allocate blocks. So from that size to maybe like 4K or 8K, you usually have buckets pre-registered. If you're out of size, you just pick a new one, create a new bucket. It's still doable. If you're really unlucky, you're out of memory on your process. This is not the end of the world. That doesn't mean you're out of memory on the system. It just means that your process needs to get more heap space. On Linux, I think the syscall is called BRK to increase the heap space. On Linux, you have stuff like VM page malloc or something. But there's a system call you can do on any OS that says, please map me more heap space to the process, and then you can manage it. And then if you're really, really unlucky, there's no more physical space on your device, so you need to find RAM somewhere. Most of the computers today, they have this swap mechanism, which allows you to just write the least used memory pages to disk. So like the 25 or more Chrome tabs you have open can just be written somewhere to disk. Meanwhile, your application can find more memory to run. But obviously, that implies disk I/O. And here lies our first problem with malloc, right? Because as you might see, there is a golden path, and there's kind of a horrible, terrible, please no path. Because the first one is, again, I don't know, if I just have a bunch of blocks sorted by like a power of 2, and I just need to find the first bucket in there and then return it, I haven't done assembly in a while, but even if you write it in C++ and optimize the hell out of it, you can probably run that in a couple cycles, like 10, 50 cycles, just an order of magnitude like that. It's not the end of the world, really. It's fairly fast. Index by bucket size, then return the first entry, done. Okay. But if you have to go to the next one, which requires you to allocate a new thing from your list of 3 pages, and then put them in that list, and then maybe you have to set up some data, and then you return the first one. I don't know, it's not an entire exact math, but roughly speaking, it's going to take you about 10 times more, right? Because instead of just grabbing the first entry in a bucket and returning it, you need to allocate more buckets, put them there, blah, blah, blah. If you start doing a system call, I think you take another 10x time because you have to switch process contests, you have to invalidate a lot of memory mapping, you have to jump into the space of the kernel, which has to access the hardware mapping unit of your CPU to map pages, and then it has to throw away a bunch of cache registers because the memory mapping of the logical and physical unit of your CPU. Lots of assembly talk and OS talk, but roughly speaking, assume it's another it's a 10x. And then if you're really unlucky, you have to write to disk, or worse, if your swap is on a network drive for some reason. I saw that recently. Somebody realized that you can have almost infinite RAM on your PC if you map Google Drive to your swap space. It's not fast, but you can literally download more RAM. Don't do this, please. So I don't know. Hopefully you're using like an M2 drive or an SSD. If you're unlucky, it's like a 5,000 RPM like hard drive from the eras, and you can hear the malloc just trying to write bytes and give you space, and then it's going to be painful. And the main problem is every time you call malloc, you don't know which of those 4 is going to happen. Unless you have a perfect understanding of the entire state of your machine, and including the kernel space and everything else, you can't really predict which one is going to happen. You can try to over a lock or things like that, but you can't really guarantee that it's going to happen. And so I guess guideline number 2, malloc is really fast, except when it isn't. And the problem is you can't tell when it isn't. It may or may not happen. There are tweaks you can do, but mostly it's unpredictable. So what can we do about this if we don't like it? If we don't like the way that malloc is unpredictable? Well, If it's just about like managing a bunch of free blocks per like size and then a bunch of pages that are mapped to your process, technically it's all library, right? Like that, it's all done by your library. So if you don't like the way your C library maintainer does it, you can be like every good game developer and be like, I can do better than those nerds at Microsoft, and just try to roll your own memory manager. Virtual memory, paging, all that stuff, that's in the kernel. I haven't seen game developer go as far as like, well, those guys at Linux don't know what they're doing, I'm going to make my own OS. But, I mean, unless you're willing to go all the way there, that you're out of luck. This is how memory mapping and swapping is introduced and managed in your kernel. It just you have to live with that. So again, you can replace the first one. Which brings me to the magical slide where I rant quickly about Microsoft. So I worked in games a lot of the time, especially when I cared about performance in the past like 7 years. And turns out the default allocator that comes with your MSVC is not very good. I would almost say it's bad, but let's stop at not good. Just because this is recorded on YouTube. And hi, Microsoft, I'm consulting if you're interested. Anyway, so one of the first things you know is that if you do debug builds, free of null, which is defined as a no-op in the standard, actually locks a mutex on Microsoft. It doesn't seem like a problem until it does, because you would assume that they do first like if null and then actually do something. No, they do the opposite. They lock the global like CRT mutex for RAM, then they check if the pointer is none. They'll then lock the mutex and return because you try to free a null. So yeah, I hated that I had to teach juniors that free of null should not be a thing you do and you should check for null yourself because that goes against what the standard tells you. But it is a reality. And also, since there are mutexes, that tells you the second problem, right? If you have two threads who try to allocate memory, even if you don't need to go all the way to the kernel, you will probably incur a lot of lock contention because there's a lot of locks everywhere. Luckily, there's a solution. A bunch of people have banded together and made a great GitHub repo that has a solution. It's a drop-in replacement to malloc-free. You can inject it by linking it to your application. My favorite is called memalloc. I've used it in a bunch of my games. It has a lot of very smart things to have like per thread blocks that are allocated, plus a mechanism to be able to free a block that was allocated by another thread without locking. I have no idea how they do it. There's a whole research paper you can read that is really smart about how they do it. Wait a minute, who wrote this? I've heard this name. Wait a minute, what? Oh, wait. Okay, so it turns out Microsoft knows that their allocator sucks, and they sponsored research into making a better one, but for reasons that I cannot really know, I can only guess, they haven't rolled that back in the default builds of MSVC. So if you're on Windows, I guess the secret message from Microsoft was not that secret, it's just use the other one. It's not the default, but trust us, we paid a lot of research for this, and it's really better. If you're on Linux or Mac, I don't know. I mean, you can use memalloc on Linux and Mac. Actually, it is possible, but I mostly focus on trying to improve performance on Windows. So I'm still pretty sure you can get some gains because this is research from the last, like 5 years. So unless that all of that has been rolled into like Heaps on Linux and whatever's the equivalent on Mac, you probably can still see some benefits. Cool. So yeah. Guideline number 3, prefer third-party heap implementation on Windows. It's just, you will save yourself some pain. All right. Now that we are out of the very basic like OS consideration, I'm going to show you a bunch of code that I've collected over the years, and we're going to try to walk together about why is it bad because of memory allocation, and especially because of the performance of memory allocations. How did I manage to gather such a set? Well, I was a senior and then a tech lead at a company for a number of years. And for a long time, everybody else was not really motivated by reviewing candidate tests. So I did a lot of those, like a lot of them. So I have seen a lot of people trying to implement a Pathfinder, which is basically the test that got you through the door and into an interview back in the day. And I've kind of kept mental notes about the interesting ones, either when they were way too fast or way too slow compared to the stock solution. And surprisingly gives you an interesting amount for such a simple exercise as writing like an A* or a breadth first search algorithm. Gives you an interesting amount of how to use memory. So, Has anyone here ever written a Pathfinder? Like even in school? Okay. Okay, so half the audience. It's fine. I have a few slides to, not even like one slide to remember how that works, right? So you have like a grid. Say you have a 2D grid, and you're trying to find the path from like point A to point B, so x, y coordinates. And the only thing you need to know is like, can I go from a point to its neighbor, or is there like an obstacle along the way? So, you know, if you start with a cell, right, and then you check its neighbor, and then you filter out, are they within the bounds of the map or not, because you don't want to fall off the edge. That's one of the two errors that people make when they make a Pathfinder. And the second one is it actually traversable or is it a wall? All right. Once you've done both of those things, you can filter out. Okay, where are the places I can go through in the maze or the map? So we can write that. It's a very simple algorithm, right? We just need like a return all the points that are the neighbors of a given point, right? Assuming that a point is a struct of x and y. So let's write the code, right? We're just gonna have a vector of neighbors because we can have an amount, and then it's a slide where so I skip the traversable check, but it's the same idea, right? Okay, if I'm not on the leftmost side of the grid, then I can go left. So I push that. Then I check same thing. If I'm not on the rightmost side of the grid, then I can go right. If I'm not at the top of the grid, I can go up. If I'm not at the bottom of the grid, I can go down. This is very basic. Let's not fall off the edge. Cool. Sounds good? Who has a problem with this? I see 1, 2, or more. What's the problem? Well, there's not going to be duplicates here. Yes? Thank you, it's fine. Second observation? You're only ever going to have 4 points. Yes, you're jumping ahead, but yes, technically speaking, I have an upper bound on how many points can happen. So I could probably use an array as long as I can return a size to go with it. Yes, Richard. Oh yeah, there's a copy paste error. That's also a problem. That's not a performance problem, but that's a problem. Thank you so much. All right, but we're talking about memory allocation here, right? So vectors is an interesting container which has this very funky thing called growth factor, which guarantees that you grow the vector with some kind of usually not a power of 2 exactly. There's a lot of math research to what's the factor you should use. People argue 1.5 or 2. Doesn't matter. Roughly speaking, it means that it's quadratic in growth-ish, so that you avoid having to reallocate all the time. But still. So we start with an empty vector, right, at the first line. So we need to add one element. The size is 0. We want a capacity of 1, so we allocate one element on most implementation. Then we try to push a second one. 2 is greater than 1, so we need to allocate again. This time we allocate for 2 because we multiply the size by 1.5 and then make sure we actually grow. Then we allocate again because we have 3 members we're trying to push and we only have size for 2. This time with the growth factor, we usually end up on like maybe size 4 or 6, depending on how it works. Either way, at least you don't have to allocate a 4th time. But each one of those times, that's, if you count correctly, that's 3 mallocs and 2 free to add up to 4 points to a vector. That's not very efficient because remember, any of those can end up swapping to disk because Chrome is eating too much space on your second monitor. So how do we fix it? Reserve! Wow, you've seen those slides before? Thank you. Cheating. Anyway, yes, reserve, since again we have an upper bound, the easy way out of this is to say, okay, you're never going to have more than 4, just allocate once, and we're done. That's great. So, 4th guideline. Reserve final container size when known rather than rely on geometric growth, because geometric growth will try to save you from yourself, but it doesn't work for that kind of process. But of course, for every rule, there is an exception. It is actually surprisingly easy for programmers to abuse reserve, I've learned through code reviews and performance investigations. Let's try to step back a bit. Okay, we have our functions that it just gives us all the neighbors to a given point. And usually those algorithms work with a queue, where you just keep adding points to the queue to explore. So let's do that, right? We are given like a list of points that we found, and we want to add them to the queue. Well, it's easy. We just reserve, because we're told that reserve is great. So we reserve the current size of all the neighbors plus whatever we want to add, and then we do a start copy, blah blah blah, with back inserters, and that's amazing. That's not great, right? Do you see the issue here? It sounds. I want to add up to like 4 points to these vectors. So I say, okay, the guideline you just told me, Matthew, is reserve the final size when I know it. And I know the final size. The final size is the current size plus the size of the thing I'm adding to it. That sounds like a good idea. The problem is when you do that in a loop, you allocate and then you allocate, and basically what you end up doing is you destroy the main reason why there is a geometric growth in vector, because you force it every time you append to it to grow by up to 4 instead of doubling. And again, it's gonna probably be fine for the first couple times, but as it grows, you can notice the red line is what happens if you have this reserve line. It's the number of malloc and frees you're gonna do. The blue line is the amount of malloc and free you're gonna do if you don't call reserve. And surprisingly, I've seen that a lot. People trying to add a collection to another one in a loop, and then don't realize that they're just killing the geometric growth by doing that. So I guess the counterpoint to the previous guideline is do not use reserve with a constant delta in a loop, because you're killing the growth factor, and that's basically shooting yourself in the foot. All right, let's zoom out a bit. So if you've never written a Pathfinder and you still want to apply to a certain gaming company, here is how you do it. So you have a search queue, right, which is all the points that you need to search through to try to find the exit from the maze. So you start with a search queue with usually like the starting point, and then what do? You get the top of the queue. You have to do top, then you have to do pop, because for some goddamn reason there's no function that does both in one in the standard. Then what do? For every neighbor that you can find, you do some code. Basically what you do is, have I already seen this point? If not, add it to the queue, maybe give it a score, etc., etc., etc. Who has a problem with this? Aha. What's your problem?
The const point P is doing it should be a reference.
Yeah, I guess you could take. It's always like probably depending if it's going to be passed by register or not. It probably is not. It's always one of those things that I never know if can I have, please, if there are standard committee people, can I have just a struct of 2 ints and not have to figure out if I have to pass them by reference or not? Hello, Richard. I was hoping for an answer to my rant about the standard, but you are correct. You are correct. We are allocating every time. Because find neighbors, as we explained before, returns a vector. Even if it's reserved, it's still we allocate every time we spin through the loop. And when you get to the point in the test rig that tests on a grid that is like 1,000 by 1,000, like a million empty points, we are going to see that you spend more time in malloc than doing anything else. And as it turns out, you don't need to do this, because we already know that every time we call find neighbors, we're going to add up to 4 elements to a vector and then clear it and do it again. So how do we fix this? And this is probably going to lead to the most controversial guideline in this talk, because I know that a lot of people hate those. But hey, how about we make neighbors an output parameter and we return void? I know functional programmers are already screaming. So we do the same thing basically. You just notice that I removed any mention of reserve, any mention of anything. This is a dumb function that says add to this collection all the points that satisfy a predicate. You could argue this is a very weird version of like copy if, but this is basically the idea. And then the outer loop, well, we put the neighbors outside of the global scope, right? We do it here, and then we do a clear every time we're about to loop, and then we just call find neighbors with this, and then we do the same code, and then we're done. And it will allocate usually once. Okay, technically, since we haven't done any reserve, it might allocate up to 3 times for the entire duration of our Pathfinder. If we're looping through 1 million nodes, it does not matter as much as it used to be. And so, again, that's the one that usually infuriates people when I do this talk. Prefer output parameters when you're returning, when you're adding or returning containers. I know. I see Kevin like, no, don't do it. I know. I've tried to walk the walk and talk the talk. I don't have a way to return a container without burning memory like a maniac. But people have suggested, you can. You just move in and then move out by having like a ref parameter, which is the container in, and then you return the containers. And then you have a default parameter that is an empty struct, so you can have 2 options. There are possibilities, but it's just make an output parameter. This is a collect. Oh, Chandler.
This isn't really an output parameter, though. The reason why it's more efficient is that it's both input and output. And that's a normal thing to use reference parameters for.
Okay, okay, I'm absolved, thank you. But Chandler said it, so I can just walk off the stage right now. But no, that's an interesting point. I've heard people disagree with this, but I mean, this is the way a bunch of, like, again, if you go back to like copyf or a few other like algorithm, that's what they do. I don't have anything to add. This is an input-output parameter, I guess, if you consider the buffer as in itself. Which generalized to the whole point of this entire talk, and I guess like you can stop listening after that if you want. Just reuse previous allocations when possible, because again, what we're trying to minimize is how many times you're going to call free and how many times you're going to call malloc. The best way to allocate is to not allocate. It's just reuse previous allocations. Because you will notice most of your containers, you have to be very explicit to get the memory out of it. You can call clear on it. The allocated heap is still there. You still have the capacity. You have to explicitly call shrink to fit, to tell vector or a bunch of other containers to just murder the actual allocation. You can tell it's kind of by design. It's trying to save you from reallocating that memory a second time. Which brings me to an interesting question when clearing structures. So I make video games, right? So you have this thing called the frame, and like 30, 60, 200 times per second, depending on how demanding your prayers are. You're trying to do a thing in a loop, right? So for example, for each frame, we're going to try to make a collection of all the visible entities that we want to render on the screen. Then we're probably going to have like a list of all the audible entities that are within range of hearing, so we can play a sound or a cue or something that the player can hear. Then maybe we want to have a debug message because that's nice, and we want to put that on top of the UI. Okay, right. So, and someone has listened to my talk and says like, oh yeah, it would be stupid if every frame I would be recreating the list of visible entities and audible entities with a new struct. So I should probably keep those in some buffer that I can reuse frame after frame, so I don't have to regrow the vector every frame to just collect the same, roughly speaking, collection of entities. And now I get to a pattern that maybe just is a me problem or a me and my previous company's problem, but I saw a lot of people do this to reset a structure. Because it has advantages. Well, first of all, it's very short. It's one line. And it can't miss anything, right? If someone decides to add more members later, you're not going to have the many times issue that I had to fix with someone forgetting that they need to clear a member that has been added to the struct. It can't miss anything. It will just run the default construct and then the copy assign or move assign, and then you'll be happy. This sounds amazing on paper, but it has a big problem. Because when you do this, it will throw all the memory away. And now I'm scared because I know some standard committee people right there, because I'm going to complain about why is it implemented this way. Okay, so this is how vector move assign is implemented in any library that I've ever seen. You clear, you shrink to fit, which is an explicit please murder all the memory I've ever allocated, and then you swap with the other one, and then you return. And I keep thinking, but my goal here is to save memory allocation, so why? Why don't you do this? Why don't they say, hey, if the other is not empty after I'm cleared, maybe don't throw my buffer away. because I need it. If you're just trying to assign me to an empty one and I have memory that I already allocated, maybe keep the memory I allocated. You can even try to be more smart and say, okay, keep the one that has the biggest capacity, blah, blah, blah. There are different ways around that. I haven't found any standard implementation that does this. I am not sure why. I'm sure there is at least one corner case that was discussed at some meeting or whatnot. I don't know, but it annoys me a lot because I wish it did that by default. And it does not, which is why I tell people to do the version on the right instead when we have to have this structure that is reused between frames. I say, no, don't use the shorthand that is guaranteed to not miss any item because you're going to throw a lot of memory every frame away. Instead, do an explicit clear, and please don't forget to do it. Because if you don't, you're going to have another type of problem. It's annoying. But this is how I save a lot of mallocs every frame, because especially, roughly speaking, the number of visible and audible entities, it's kind of the same from one frame to another. So it's going to grow like once in a blue moon, once I've stopped the game running. And it's viral, right? Because if I myself have like this frame data inside a second structure, I also have to make sure that everybody remembers to clear the clear function everywhere and doesn't actually do a reassign. It's viral, right? If I start saying my idiom is not assigned to empty, it's called clear, I have to make sure I teach everybody to always call clear instead. It's not the end of the world, but I haven't seen every company does have a clear method on every container, every type they have that could potentially be reused after it's been first done. So guideline number 8, prefer member-wise clear over assignment to empty struct. Again, we are trying to save ourselves from reallocating more memory if we have already allocated the memory. And that's how you do it. How much time do I still have? Okay, good. I guess I talked a bit fast. So that will allow me to take a bit more time and talk about some bonus other things like custom allocations. I will not go into detail too much because there are better talks about this, but I can give you some references at the end if you're interested into going into custom memory allocators, because what I've given you now is just the basics. I know some people in game dev Twitter would be so upset because I'm still using the STL and the default allocators in there. But it's already a good start, but maybe you want to go further, right? Because the problem of a general purpose allocator, as the name implies, it has to be good for everybody, which means it's great for nobody, usually. Can't make any assumption about how I'm going to use it, have to make compromises. What can we do about that? The first thing that people usually mention when I start talking about stack very early and say that you can't actually have like variable size allocation on the stack, they'll mention alloca. Who here is aware of alloca? Okay, for the other ones, you never heard about it from me, and basically forget it as soon as I'm done with this, because the guideline will explain to you why. So it's not standard, as far as I know, but it's very common. I mean, I've been shipping game on free platforms like Linux, Mac, and Windows, and all of them have it. So it's standard-ish, standard adjacent. And it's basically dynamic stack allocation. It basically allows you to use the stack with a size that is not known at compile time. It's a register add from another register instead of from a constant. That's what it does. It's a C API. It's a good old C API. So you're going to have to do a wrapper, macro or whatnot to be able to add RAII back. Because if you don't do that and you use it to allocate like C++ types, obviously you're not going to run the destructor. So usually what I've seen people do is have a way to allocate an object on the stack and then run a destructor custom blah, blah, blah. And it's fast because, again, what it does for the part that is the malloc, it's a register add. So we're back to like, this is the fastest thing possible. You could technically do that to say, I need an array of like X elements. You could do that with alloca. It comes with some problems. First is bound by your stack size, right? Again, we'll go back to the famous Stack Overflow problem. It's a very easy way for people to blow the stack, especially if someone calls alloca and then within that stack frame calls another function that also does alloca, because you have no very easy way to see how much has been eaten so far from your program stack. And so, for example, I've seen people try to optimize my Pathfinder by not using the size of a vector and just allocating the grid with alloca, which works until the grid gets too big, and then you run out of RAM. Not out of RAM, sorry, you run out of stack space. If you're lucky, it will be caught. If you're not, it's just gonna immediately like randomly crash or do some funky things. Again, limited space, especially on threads, especially on new Mac. Yeah, if you didn't know, on Windows it's not an issue, but on Mac, threads have a way smaller, non-main threads have a way smaller stack size by default. That is kind of painful to change, and that will bite you if you start throwing like jobs on secondary thread that happen to use alloca. And again, for some reasons, you cannot set the size of a stack of a thread with the standard C++. You might be able to do it with a custom library, but if you use a steady thread or JThread for that matter, it's impossible to set the stack size. I know there's something about stack size and blah, blah, blah. Anyway, you can't. So for all those reasons, I would say, forget what I just said about alloca. Forget the colleague who suggests that you should use alloca here because it's likely to overflow the stack eventually. In general, I would not go that route, even if I have to mention it because you might just run into the argument one day. Instead, you should look at custom allocators. And that's the part where I'm not going to talk too much because there are better talks about allocators, much better talks and many more. So, you can have special purpose allocators. Basically, instead of calling malloc, you can call your own custom allocators, who either does different allocating strategy or has a different like a pool that is reserved for itself. You can do a lot of things with that. You can decide what malloc does for a subset of types or a subset of allocation, and that allows you to roll out your own way of doing things. And one of the big ideas is that you can try to say, okay, malloc has some constraints that I don't need, and if I chuck them away, I can gain something out of it. Again, if you want to know more, my favorite talk on the matter and the one that introduced me a lot to this is Andrea Weiss, Taming Dynamic Memory. I usually go back to this every time I have to talk about allocators to people. It's done at ACCU 2019. It's a pretty good talk. Feel free to go and check it out. But out of all the options, I'll just briefly mention monotonic allocator, because the basic idea is like, what if malloc didn't have free? Or more specifically, what if free was all or nothing, which is either you free everything that malloc has allocated or you don't. You can't free individual allocation. Well, then our allocator becomes a stack again, right? It just becomes, instead of a stack, we just take a big vector and we say, behave like a stack. Every time I allocate, you just push to it, but you can't pop. You can only delete everything, and that's all. It's as fast as stack allocation, as I mentioned, because once your buffer is set up, the only thing you need to do to allocate with a monotonic allocator is increment an index or a pointer. And yes, what you give up is the ability to deallocate a given object. You can either free everything that's been allocated by this allocator or nothing. You can't do anything in between. And it turns out it's extremely popular in games. And I think it should find its way in other industries too. Actually, we have time. I can show you the slide where to implement it because it's really 2 slides. So all you need to have is like an array of bytes. I use unique pointer here. You could technically use vector, but since we don't need to resize, a unique pointer of bytes is good enough. You have a pointer to the current one. You allocate it with a given size at creation, and you store where the start is, which is your current pointer. And then you have an allocate function. Don't be scared about the math. It's just there to handle alignment. Basically, we round the size that you're trying to allocate to the minimum size to the alignment that malloc is expected to give you. And then we just do an add. This is literally more code than what the assembler would generate out of this. Like instruction in the assembly is going to be like maybe 2 or 3 things, like an add, an or, and another add, and you're done. Deallocate is extremely easy to implement because you don't have to do anything. And deallocate all is almost as easy. You just reset the buffer to the start and you're done. And you've deallocated everything. So basically, when you can budget and control the scope of your allocation, it is amazing. For example, if you have a game level and you say, okay, all the assets that pertain to this level, I'm just going to add them to this bucket, and then when I'm out of the level and load the next level, I can just throw everything away and then start over with the next level. And that's it, because I will not have to unload individual assets. It doesn't make any sense. I can just throw everything away. If you have a state machine, or if you do like any form of transaction or request processor, like a web server, for example, or any kind of like web server, like any backend thing that just has an API call, has to do a thing, and then return at the end. You can say, okay, for the processing of this request, I have this this allocator. All the allocation it will need to do its job can just go to this, and then once I'm done handling this request and I send the response, yeet the whole thing out. In some games, we even push it further and we just make sure that we only use it with types that have no destructor. So I don't even need to run any destructor. I just forget that those objects ever existed, and then we start over. So this is my last guideline. Maybe I have the bonus one after this. Consider monotonic allocators when resources can be scoped and budgeted, right? Because you need to have an upper bound. Remember, we implemented this with a unique pointer of bytes. What happens if you try to push further than the maximum size? Bad things happen. So you need to have a scope. In games, this turns out to be great because this is an amazing way of enforcing what we call budgets, which is to say, okay, for our game, for this level, you allowed this amount of memory for I don't know, like models, this amount of memory for audio, this amount of memory for like dynamic object or monsters or whatever. And if you go over it, it will crash. And that's not a bad thing, because the alternative is you don't, and then the lab comes back and say your min spec needs like the dwarf to go back to Moria to build your computer because nothing else can run it. So it is good. It is a way of enforcing a guaranteed budget. If your boss, like another company has worked out, says, no, the main thing is this app never crashes no matter how bad we go, this is not as great. Just as a warning, if you start playing with allocators, you can start saying, oh, but I can fix those problems. I can like start allocating more buffers when the first one run out, or I can have like a least or last like a free list on the side. I did not put the slide here because I was worried I will not have the time, but the secret guideline after this is every time you try to go further than this, you get dangerously close to try to re-implement malloc. And this has happened more time than you think. So be worried. Like monotonic allocators, yes. If you go further, you're basically trying to roll out your own malloc. Right, so try to get a conclusion and maybe take some questions. So dynamic allocation in the end comes at an unpredictable runtime cost, and we're trying to alleviate that by reusing memory as much as possible. So size up allocation if you can, so you allocate once instead of allocating in a small increment. And reuse container as much as possible, because that way you don't have to call malloc. Consider monotonic allocators, but beware, going any further, you start re-implementing malloc. And furthermore, I still think your build should be destroyed. Thank you. I will take questions.
So you mentioned that you can't set the stack size of threads in standard C++. So the standards committee is working on that. There's a paper P2019. It unfortunately missed C++26, but in C++29, you should be able to pass a type called std_thread stack size hint to the constructor of std_thread and jthread.
Interesting. I solved the problem by having a monotonic allocators per thread and just say, hey, this is your local buffer if you need to do stuff that has to go fast and then you throw away. But that's an alternative.
So I believe it's in contract for reserve to reserve more memory than you strictly asked for. Do you know if that's correct?
So that's an interesting question. I think I had a slide about this, but I cut it for this duration. As far as I know, unless this has changed, and maybe there is like a paper to change that, you have no way to tell reserve, are you using the exact or are you using the growth factor? I know some alternative versions of containers, like for example, like alternative STL reimplementation that we love so much in games, usually have a bonus parameter to reserve that is use either the exact size I give you or use either the size I give you or the next best growth factor. I believe the default right now is unspecified, question mark?
I wasn't aware of that new parameter because I'm honestly a bit surprised. Like, obviously, if I have an empty vector and I ask for like 500 megabytes, I wouldn't want it to reserve a gigabyte, maybe. But if I already have 200 megabytes and I say, can I have 204 megabytes, please reserve me, I wouldn't, I would feel it's a reasonable choice to say, oh, quit screwing around, have an extra 10 megabytes.
Yeah, as far as I know, and I've looking up at the implementation, reserve right now gives you the exact size unless you already had that or bigger, and then it does nothing. I wish there was a way to say, use either exactly what I say or grow up to include that amount of size. But as far as I know, it doesn't do that right now.
Okay.
And you have to roll your own. No more question. What's your favorite Shakira song? I don't know. Ah, there we go. What's your favorite Shakira song?
This is probably. Oh, sorry. This is probably down the completely different bizarre road. That's more like re-implementing malloc. But I remember in the olden days for Mac programming, you never allocated a pointer to heap data. You always allocated a handle, which was a pointer to a pointer, which I guess was to allow the Mac OS to do fun things when you wanted to allocate memory to perhaps more quickly move free memory lists around. Do people still do tricks like that?
I don't know of any of that, no.
Okay, it was just curiosity.
Benefit of custom allocators is if you have your own little pool of heap, you're almost guaranteed that it's going to be cache local. So it operates much faster than randomly somewhere else in memory.
Yes, because even if technically, usually malloc implementation try to keep stuff of the same size in sequential buckets, you're not guaranteed that they're all going to be in the same way. And I think it's a thing that we've in another era, I studied operating system design, and it's a thing that they do in the kernel. For example, they have like a custom allocator for different type of object. It's also sometimes done in games, especially like if you watch my ECS talk. That's one of the things we do, which is like, okay, this is a collection of monsters. I'm just going to have a bucket of monsters. So then we guarantee that all the monsters are next to each other in memory, even if we can't put them in an array, even if we have to put them in like any form of list or map. At least you can somewhat alleviate the cost of jumping from one to another because they're still somewhat in the same memory area. Still not as good as putting them in a vector, but again, watch my ECS talk from last year if you're interested. Aha. Yes, Lars Bob?
A fun trick I also use when you have a graph of heterogeneous types is to use a monotonic allocator so you can really shrink your pointer size because you can change it to a 16-bit index instead of a 64-bit pointer.
Yeah, that's a trick. I've also done it in places when you want to do buffering and you don't want anything to be absolute address. You can use that trick to make everything a relative address, for example. So if you have, like, you want to do a double buffering with like deep reference to different objects, you can say just save the offset to the object rather than, because technically a pointer is an offset from 0. You can make it an offset from an arbitrary size if you want to do funky tricks like that. Memory map file. Oh, that's another. Yeah. I've seen that. All right. Thank you.